Our next session is going to be looking at sustainable water supply from a technology point of view. And I think we've heard about some of those technologies leading up to this discussion, but we'll be focusing in on specifically here. And the moderator for this session is Meny Elimelech. Meny is at Yale University. Prior to that, he was at UCLA, and I know several of his students are here as well. Meny is a former Clark Prize recipient. It was before my time. I'm sorry I missed that, Meny. I wish we were videotaping him back then. But Meny, please come on up. I appreciate you being here. Thanks so much.
Okay, good afternoon. I know it's a tough time and session immediately after lunch, but we will do our best. So welcome to session 2 on advances in treatment technologies for sustainable water supply and development. I think this session tied very nicely to David's talk on Water 4.0. So we have 3 talks today, and we'll hear about a municipal water system, mostly on the process and system engineering. Then we will hear how we can combine nanotechnology with membranes to get an even better process, more robust process. And also we will have a talk on advanced membrane technology, mostly emerging membrane technologies that can play on the water energy nexus. So you will hear a lot about water and energy. So with this short introduction, I would like now to start to introduce the first speaker. The first speaker is one of the legends in water quality engineering. It's Vern Snoeyink. Vern is an emeritus professor. He was the Ivan Ratchev Professor for Environmental Engineering at the University of Illinois. Vern won the Clark Prize a year before me, in 2004. And he's won many awards for his research. He's a member of the U.S. National Academy of Engineering. He educated a large number of students that play a very critical role in industry and academia, including some of them are here. And he also developed a lot of processes that we can really see them in practice in water and wastewater treatment plants. So welcome, Vern.
So I'd like to talk today about municipal water treatment, recent advances, and drivers for change. When we talk about a major advance, I'd like to consider it in terms of the numbers of entities using it, the beneficial results that come from it. But in doing this, I would also point out that incremental advances are very necessary in order to make seminal research a major advance. Some examples. So certainly I would put membranes and membrane processes on the list of major advances. I think everyone here would agree with this. 1960, when the membrane, asymmetric membrane, was invented or was developed at UCLA, since that time we have had many advances in the areas of membranes and module configurations, the areas of filtration, membrane filtration, microfiltration, ultrafiltration, and then also nanofiltration and RO. And we've had a lot of things that have been done in terms of pre-treatment, post-treatment, and energy efficiency, all important in making membranes a major advance. So some data to make this point a little more clearly. So RO capacity versus time. So certainly since 1960, there was 20 to 30 years there where not much happened after this first membrane was developed. But then things started to take off, and 2010, 60 million cubic meters per day total capacity, and we're on a rapid increase from this point on. Major advances have been made in the area of the reduction of the energy required per unit volume of water product. So you can see 1970, 12 kilowatt hours per cubic meter. That's probably one of the reasons not many folks were putting membrane systems into place. But certainly that's come down nicely. The 2006 number here on this graph, this set of data, is 2 kilowatt hours per cubic meter. Now this number is something that shifts around a bit depending upon recovery, composition of the water, and whether or not you include pre-treatment and post-treatment. Taking a look at the desalination plant in Barcelona, Spain, on the Llobregat River, for example, you see lots of pre-treatment processes there. The water is taken out of the open sea. It goes through flotation, gravity filtration, into a two-stage RO system, and after the RO, there's a remineralization step where you add alkalinity and calcium to the water prior to distribution. There's treatment of the effluent from the microfiltration pre-treatment system. So sludge disposal is necessary, and then brine disposal. So there's a lot of aspects associated with getting salt out of water. So it's 3 kilowatt hours per cubic meter is what the folks in Barcelona would say they're using, and then add 1 kilowatt hour per cubic meter to that amount of energy for the pre-treatment and post-treatment for a total of 4. The membrane filtration capacity has really taken off as well. So, but it did not happen until after the turn of the century. So we see now that membrane filtration capacity 3,700 MGD in 2010. So this is an important market for the U.S. membrane industry, and this is going to increase very significantly in the future. So membrane filtration is a major process for us. Investment in the bioreactor market. I think this is very interesting as well. So we look at the dates, again, about the turn of the century is when the bioreactor market started to take off, and now we're at $600 million a year investment projected for 2015. So things are moving along very nicely. I would put UV disinfection in the area of a major advance as well. So our drivers, as most of us are aware, the protozoan cyst that's in drinking water, and toxicity in secondary effluents, getting away from the chlorination of secondary effluents, using UV instead. We note that UV capacity versus time has increased very rapidly as well. So 20% or 4,000 of North American wastewater plants used UV in the year 2008. So certainly UV has its place. Ozonation, very important process for us. It's used for taste and odor, disinfection byproduct control, disinfection, synthetic organic compound oxidation, and often in conjunction with hydrogen peroxide. There's also uses as a coagulant aid and for color removal. Water treatment plant use, 4,000 plants worldwide, 250 of those plants in the United States, and the timing again on that is about 2010. So ozone is here. So a recent paper by Garrity in conjunction with Rhodes Trussell reviewing flow diagrams that are used at water reuse plants throughout the world. The one process that's in all of these plants is ozonation. So a critical process for us, and certainly looking over the years, this has been a major advance for us as well. I'd like to switch gears just a little bit and look at some drivers for change. We heard what a number of these were this morning. Certainly climate change is going to drive things for us, and a number of other aspects related to water availability and so forth. But I would like to take a look first at regulations. Regulation is a very important driver, and sometimes it drives us in the wrong direction. So it's for disinfection byproducts, for example. We have the THMs at 80, ppb or micrograms per liter, and HAAs at 60, and nitrate nitrogen at 1 ppm. Now these levels are very important. Measurable disinfection at the tap. So what has this caused to happen? So monochloramine for secondary disinfection, maintaining a residual in the distribution system. About 1/3 of our utilities in the United States now use monochloramine. But this nitrification is a very significant problem for many of our utilities. So the monochloramine gets reduced, ammonia is reformed, nitrification takes place, and we produce nitrite and nitrate. So about 1/3 of utilities that use monochloramine have nitrification problems. DO loss, chlorine loss, nitrite increase in metal ion release, and there can be additional problems to those. So there's, without a doubt, monochloramine has worked well for secondary disinfectants for many of our water treatment utilities. It's been a success. But for many of our utilities, it probably was the wrong way to go. And I would not, and from my point of view, I would not put this in the category of a major advance, because I don't think it's being used correctly in a lot of situations. So the water shortage, we heard a lot about that this morning, and it's driving us to use water that has much poorer quality, that is of much poorer quality. It's driving us to direct potable reuse, and certainly it's affecting what kinds of processes we're going to be able to use to purify our wastewater. The increasing amounts of treated wastewater and urban runoff in our water supplies recommend the NRC report, 2012 report, that was produced with Rhodes Trussell as a chair, and other members here in the audience were members of that committee. But reading this report, I think this is one that's going to be very influential in affecting the direction that our nation takes as far as water direct potable reuse is concerned, and also indirect potable reuse. So that report, by the way, is available free of charge on the National Research Council website. So water shortage versus treatment. Well, it's certainly, I would say, what sort of process can we use to take out these contaminants that are there from this poor quality water that we now have to treat. On the coast, we'd have the possibility of discharging to the ocean, but inland, concentrate disposal is a very serious problem. So if we'd operate our RO to get 75 to 80% recovery, we've got a lot of concentrate that we need to dispose of. Terms like zero liquid discharge are coming into our vocabulary, water treatment industry vocabulary. So it's zero liquid discharge. It's very expensive and complex. I'll show you an example of that in the next slide. But a lot of folks these days are talking about near zero liquid discharge, treatment of RO influent and RO concentrate to achieve a net overall recovery in the range of 95 to 98%. So certainly an exciting area of research. Zero liquid discharge, the one example that I'd like to talk about for just a couple of moments here is this 0.14 MGD system that's now being constructed in Pueblo, Colorado at a chemical demilitarization site. So it's chemical weapons certainly these are very much on our mind as far as Syria is concerned today, but it's the U.S. still has a couple of stockpiles of chemical weapons that it needs to complete disposal of. So it's building a zero liquid discharge plant in Pueblo, Colorado to take care of this. So basically the process sequence is to hydrolyze the chemical agent, take the organic matter that results through a bioreactor, then to evaporation, crystallization, and production of a dry cake by belt filtration. What we're hoping will come out of that is shown in the picture at the bottom of the slide. That would be what we would call a dry cake, but certainly a certain degree of moisture is associated with that. This is the flow diagram, so just let me make a couple of points relative to this diagram. So the evaporator feed comes from the biotreatment system. The pH is lowered, you would go through a deaerator to strip off the CO2, raise the pH again and put it into an evaporator. This evaporator is a real monster. So 596 50-foot long tubes for evaporating the water and getting it down to the point where precipitation will just start to take place. The distillate is processed through activated carbon for reuse within the plant. And the concentrate out of the evaporator is taken to the crystallizer where steam is again used to produce a slurry of particles that can be dewatered on a belt filter. So this plant is not running yet, but it's nearly ready to run. It'll be very interesting to see just what kinds of results come out of this. The bottom line in all of this is that whenever we get to the point of having to use an evaporator or a crystallizer and start using steam to bring this about, energy use is very, very high. So near zero liquid discharge in water reclamation for using reverse osmosis. So here we take bioreactor effluent. There are plants in operation that are using this kind of approach. But when we want to get the additional water out of this concentrate, we talk about processes such as lime softening, pellet softening, seeded precipitation of calcium sulfate, maybe a cation exchange process, electrodialysis or electrodialysis metathesis. We get some interesting names here. Ozone and BAC, because there's organic matter that's being concentrated in this RO unit, and if we're going to further concentrate, we need to be concerned about membrane fouling with the organics. Capacitive deionization is another process, and then secondary RO. So a very long list of possible processes. Now, from a person interested in research, it's interesting to take a look at these and say we could have a good time figuring out which ones to use, because all of these processes, which ones you use, are an important function of waste composition and the desired water quality. The bottom line, though, is still, when you get through with all of this, you still have 5 to 7% of the water that's influent that you have to dispose of. So this hasn't completely eliminated our problem of using RO and inland processes. Okay, the concentrate disposal. One question that you can raise is, do we really need RO? One report from Lee et al. From working with Kerry Howe at University of New Mexico, and Garrity et al., a team under the direction of Shane Snyder, now at University of Arizona, looked at this issue and said, look, if we take secondary effluent and do a good job with ozone, biological activated carbon, perhaps ozone with hydrogen peroxide, inactivated carbon, we may be able to treat the secondary effluent to a quality that is suitable for many reuse applications. Now, certainly, you would like to have that barrier that RO gives you, but it's possible that this approach of leaving the salt in the water is a better approach from the standpoint of how do you dispose of the concentrate if you don't? How do you dispose of the concentrate if you do use RO? These two reports showed excellent removal of many of the trace organic compounds that we're concerned about. Energy is also a major driver, so RO for desalination. So is desalination with RO the best way to go? There's a patent by Siemens that's in the patent literature that was developed in response to a request for proposals by a challenge proposal by the Singapore Public Utility Board. So they said a typical requirement, energy requirement, is for including pre-treatment and post-treatment for RO. A typical energy requirement is 3.5. So the challenge RFP was issued to develop a process that could cut that in half to 1.75 kilowatt hours per cubic meter. So this patent was developed in response to that. So ion exchange, electrodialysis, and electrodeionization were the three processes that they put together for this operation, and they pilot tested it. Now, this process scheme is not on the market as yet, but it does raise an interesting question. If this concentrate disposal is important, well, certainly we get concentrates from these other units, but if energy is important and concentrate, we can get smaller amounts of concentrate and we can get lower energy by using processes that take the ions out of water rather than force water through a membrane and leave the inorganic ions and organic molecules behind. Okay, so recovery of energy from municipal wastewater. I'm not going to talk about that. Professor McCarty covered it last year. The personal conversation with him said that process is going great. It's basically the anaerobic membrane bioreactor with the membrane filtration immersed in a bed of fluidized granular carbon. It's going well. There's a number of pilot plants in operation, and this looks very promising. So certainly we need to use our wastewater as a resource and this energy resource that we can get from not using aeration in an activated sludge process, but using instead anaerobic digestion, anaerobic processes to reclaim energy. The largest amount of energy makes a great deal of sense. Distribution systems, I would also add to my list of drivers. You may have your own list. Certainly, this is not an exhaustive list in any respects, but distribution systems, I think, is a very important consideration as to what we do and how we do it. Whether we're using a centralized system or a decentralized system, we need to transport the water, and the materials that we transport it through and their interactions with the water that we're distributing is a very important consideration. So I've shown you three pictures in the bottom of this diagram. So the one on the far left, manganese deposit in a drinking water distribution system. We then have an online cast iron pipe and lead. There's good indications in all of these that microbes play a very important role. So I think as the folks that are now actively involved in the microbial ecology studies in distribution systems, I'm expecting some big advances to come forward that will help us control these kinds of problems in distribution systems. Okay, so the final thoughts. Certainly there's been a lot of major advances that have changed the way we treat water today, and are drivers that are going to have a marked change in the way we do things in the future. My own perspective is that this is an exciting time to be in the field because of the research and development that is needed to meet the new challenges. And I may just come out of retirement to do some of it. Okay. Thank you very much.
So we have time for questions. Yes, David?
So, Vern, thanks for a nice talk. You talked about two alternatives to reverse osmosis, and both involved ozone. And I would have real concerns about the bromate formation problem if the intention was to reuse the water. And to me, it seems like the reason we use reverse osmosis is a salt management problem and not a trace organics problem. And so can you tell us something about the potential to reduce the salt loading in our water supplies, and whether that would be a better alternative for inland communities to put more attention on salt management as opposed to treatment of salts?
So salt management, like eliminating home softeners, for example.
For example, and industrial uses.
Yes, yeah. Certainly, if you take as a given that every use cycle that you go through with municipal water, you increase the total dissolved solids content by 200 to 300 milligrams per liter. There may be things that can be done on the consumer side to lower that amount. I think anything that can be done as far as salt is concerned is important. Even if we use a process like ozone BAC, with continued reuse, we're going to continue to build up our salts. At some point, we have to take these salts out of the water. So certainly, your point is well taken. I would support it. Anything that we can do to reduce the amount of salt going into wastewater is very important. On the bromate side, there are going to be times when whatever procedures that we have available to us now, we're not going to be able to use ozone because of bromate.
Yes, Jerry?
Nice talk, Vern. Thank you so much. I wondered about deep well injection of the brines. You didn't talk about it too much, but are communities for the coastal communities, you said that ocean disposal might be an option, but for the inland communities, are they not able to get permits, or what's the problem there?
I listened to a presentation by folks from Denver several months ago, and they're very concerned about deep well injection promoting seismic events. So deep well injection may work in certain situations, but there's a lot of concern about the deep wells. So deep wells are not a panacea.
Hey, one last question. Yes, there. Microphone.
Appreciate your talk. Just have one question regarding the issues on the distribution systems. I'm thinking about in terms of the direct potable reuse. People have been talking about compared with indirect potable reuse, the natural barrier versus engineered barriers, or natural buffer versus engineered buffers. I'm curious about, in your opinion, what will be your view on the distribution systems in direct potable reuse as a engineered buffer, or for beneficial applications for reused water quality?
If we have direct potable reuse, we're going to treat the water so we can drink it. So it's, I don't see that the distribution systems are going to play much of a role there, except in the instance that we don't treat it properly and we put biodegradable organic matter into that distribution that can support the biofilm growth and the degradation of water quality that goes along with it. So, I think certainly with the dual systems where we take secondary effluent and say we don't have to treat it as much if we're just going to use it for toilet flushing, for example, or lawn irrigation. I think the degradation of quality is a very serious issue in those pipelines. So what happens to that water in those pipes?
Okay, thank you.